As promised in the previous video lesson, here's an example problem of a combination network of capacitors, and let's try to figure out what's the total amount of energy stored in the 6 farad capacitor. Now this might be ridiculous values, right? Farad is a very large value of capacitance, so you'd be hard pressed to find a 15 farad capacitor, but just for the sake of solving this problem, we'll work in full farads instead of microfarads or picofarads and so on. Okay, so the first step in solving problems like this is to identify how the capacitors are connected. In other words, how is the 20 farad capacitor connected to the 5 farad capacitor? There's no correct answer for this. They're not connected in parallel, they're not connected in series. They don't have any simple connection between the two. The only simple connection here we should probably start with is that the 30 farad is without a doubt connected in series with the 6 farad. And that combination in turn is connected in parallel with the 15 farad and so on. So a good idea is to just picture reducing the circuit down into simpler and simpler versions until you have it reduced to just one single equivalent capacitance. Now, I don't really need to draw in the battery here. Let's just say that this is point A and this is point B. Before we get too far, let's see if we can agree on what the value of electric potential is at every point in the circuit. So I know the electric potential here is 0 volts because that's the symbol for ground. So I can show all the points that are at 0 volts. Anything that's connected by bare wire to that point must be at the same electric potential. So everything you see here in blue represents 0 volts in this circuit. In the same manner, everything you see here in red represents an electric potential of 24 volts. The problem is we don't know the electric potential at that point. Oh yeah, we do. I take that back. Oops. Oh, we're back on track. Forgive me. I can extend that point. Yeah, we know the electric potential right here is 24 volts, and likewise the electric potential right here is 24 volts. So does that mean the voltage for the 30 farad capacitor is 24 volts? No. Voltage is not just the electric potential at the positive plate, it's the difference in the electric potential between the positive and negative plates, and we don't know what the electric potential is at this point. Heck, we don't even know what it is at this point, right? So we'll figure this out as we reduce the circuit along the way. So there's our 15 farad capacitor. And then here's a capacitor that represents the combination of the 30 and the 6. And then that's connected to the 20 farad capacitor. And all that is then connected in combination. All of that is connected in parallel with the 5 farad capacitor. So we just need to figure out what's the value of this equivalent. Well, these two are connected in what? Series, right? And the rule for series, as long as you're just connecting two of them, is it's equal to the product over the sum. So 30 times 6 divided by 36 gives us 180 over 36, gives us 90 over 18, gives us 10 over 2, oh yeah, 5. Okay, so this is like a 5 farad capacitor. Well, then this 5 farad equivalent capacitance is in parallel with this 15. So if we reduce this yet again, it's as if we have a 20 farad capacitor in series with another 20 farad capacitor, and then those two are connected in parallel with our 5 farad capacitor. So we still have our points A and B can be identified in every one of of these reductions. Well, this is easy. A 20 in series with another 20 should give us a result of, don't say 40, 10, right? So we imagine reducing this yet again, and it's as if we have a 10 farad capacitor in parallel with a 5 farad capacitor. It's important, I think, to draw these A and B, because if I had A right here and B right here, then it would be like having a 10 and a 5 connected in series, and then that in turn is in parallel with a piece of bare wire that would short circuit those capacitors. But in any case, it's vague whether or not you would describe the connection as being series or parallel unless you draw in more of the wiring, right? So instead of having A and B like this, if we show that it's A and B like this, then we know for sure they're in parallel. So finally, we get to our one equivalent capacitance for the whole circuit, which would be 15 farads. So we want to use this chart to represent how we can apply the equations across any given row, and as long as we don't mix and match, everything will fall into place. So let's identify all of our capacitors. How about we start with our 5 farad, and then our 20 farad, and our 15 farad, and our 6 farad, and 30 farad. Okay, create rows for each of these. Then we need to add one last row for the equivalent. And we found that the equivalent is also 15. So as not to confuse this 15 farad with the equivalent of 15, let's just write CEQ on that last line to be sure. Well, the one thing we know without a doubt is that the voltage for the equivalent capacitance is the full voltage of the whole circuit. So we can say we have 24 volts here. And now Q is equal to CV, so if we multiply 24 times 15, that's 240 plus 120. That should give us 360 coulombs. So where's that 360 coulombs? That's the positive charge all spread out on this plate. So if we go back to the previous diagram, that means 360 coulombs is divided up a little bit on this plate and a little bit on this plate. So if this voltage is 24 volts, right, the potential at point A and the electric potential at point B differ by 24 volts. Well, this is still point A and still point B, so that's still 24 volts. So the amount of charge on this plate would be equal to 24 volts multiplied by 5 farads. So 24 times 5 gives us what? 120. Okay, well, that 5 farads is this 5 farads, is this 5 farads, is this 5 farads. So we know the amount of charge on the 5 farad capacitor is 120 coulombs. So what's the amount of voltage? Voltage is charge divided by capacitance, so 24. But yeah, we know that, right? The electric potential at this point, as indicated in red, is 24 volts, and the potential at this point is 0 volts, right? So we could have gotten that straight off the bat. No other capacitor has that same amount. But now, if this is 120 coulombs out of 360, then this must have 240 coulombs on it. Okay, now when we trace that back to the previous diagram, where's that 240 coulombs? Well, it's here, but it's also the same on every plate, because that's how it works when you have capacitors connected in series. There's charge by induction taking place. So if there's 240 coulombs on this equivalent capacitance of 10 farads, that means there's 240 coulombs on the 20 farad capacitor and shared or divided up on the combination of the 15 and 5 farad capacitors. So this 20 farad capacitor has 240 coulombs. Voltage is charge divided by capacitance, so when we divide 240 by 20, we get 12 volts. That means the electric potential right here, as we know, is 0 volts. So the electric potential right here must be 12 volts, and we know the electric potential right here is 24 volts. So, no surprise, because this 15 and this 5 farad capacitor are acting as one single 20 farad capacitor, a 20 farad capacitor and another 20 farad capacitor in series act as a voltage divider that cuts the full voltage in half. From point A to point B, there's 24 volts, but if we compare point A to the point in between the two capacitors, that's only 12 volts. And 12 volts plus 12 volts gives us the full 24 volts. So, the voltage for the 20 farad capacitor is 12 volts, but that also means the voltage for the 15 farad capacitor or the voltage for the 5 farad capacitor is 20 volts. So, I'm sorry, 12 volts. So now we want to know the amount of charge on the 15 farad capacitor. Charge is capacitance times voltage. 15 times 12 gives us 180. All right. So out of this 240 coulombs, 180 are on the 15 farad capacitor. All right. So where's the other 60? Well, it's here, or it's here. But what are those plates? That's the positive plate of the 30 farad, and it's the same thing as the negative plate of the 6 farad, which means the other plates are charged by polarization. And so if it's 180 volts, 180 coulombs on the 15 farad capacitor, but it's supposed to be 240 coulombs in total for this equivalent network. I know this is getting messy. Then there must be 60 coulombs on the 30 farad capacitor. And there's also 60 coulombs on the 6 farad capacitor. All right, so how do we get voltage? We divide charge by capacitance. So when we divide 60 by 6, we get 10 volts. And when we divide 60 by 30, we get 2 volts. Now let's see if this all makes sense. Let's clean this all up. So the potential across the 5 farad capacitor, as we know, is 24 volts minus 0 volts. And we have that here. All right. The potential difference across the 20 farad capacitor is 12 volts. So the electric potential right here is 0 volts. That means the electric potential right here must be 12 volts. The electric potential right here is 0 volts. Here is 24 volts. Let's see, the electric potential right here is 24 volts. So the electric potential across the 15 farad capacitor is 24 minus 12. So is that what we have written? Yeah. The 15 farad capacitor has a potential difference of 12 volts. Okay, so far, all of these three voltages highlighted in green seem to check out. Now let's see here. The electric potential at this point is 12 volts. The electric potential at this point is 24 volts. And we're saying that the potential difference across the 30 farad capacitor is only 2 volts. So 24 minus 2 would give us 22 volts. Alright, and then 22 volts minus 12 volts would give us 10 volts. So as that we have in our chart is the voltage for the 6 farad capacitor 10 volts. 6 farad, 10 volt, yeah. So that one also seems to check out. So I believe we have all of our voltages correct. Now I'm trying to remember what the original question was. I think we said how much energy is stored in the 6 farad capacitor. Okay, well, as long as we just work across the row, we can use any one of our equations. We can do 1/2 CV squared, Q squared over 2C, or 1/2 QV. So 1/2 CV squared would give us 1/2 times 6 times 10 squared. Q squared over 2C would give us 60 squared over 2 times 6, and 1/2 QV would be 1/2 times 60 times 10, or in other words 30 times 10 for 300 joules. 10 squared is 100, half of 6 is 3, 300 joules. 60 squared is 3,600. 3,600 divided by 12 is 300 joules. That's right. No matter which one of the equations we use at this point, we should get the same answer. And so I want to just point out, making charts of this sort are very useful when solving more complex combinations of capacitors. And I know the work might get messy along the way, but if you take the time to draw reduced circuit diagrams one step at a time and think your way back through the circuit, you should have no problem as long as you're willing to spend the time solving problems like this.